Very happy to present Jixiang. Jixiang is here today to talk about, I guess, Bayesian optimization and diffusion models. Well, he's here to talk to you guys about all this stuff, but we asked him to fill in the reading group slots quite last minute, and he was so kind to suggest to present his latest paper that just got accepted at ASS, I believe. The paper is about information-theoretic approaches to multi-objective Bayesian optimization. Jixiang is a PhD student, last year PhD student at Ghent University. Yeah, go ahead.
Yeah, thanks for the introduction, Vincent. So hi, everybody. Yeah, it's really great to have a chance to discuss this work here. So basically, we are talking about the Bayesian optimization, or more specifically, the multi-objective Bayesian optimization. So we proposed a new acquisition function based on the information-theoretic. That will be the main topic of this presentation. And this is a collaborative work with Henry Moss from Second Mind, also Tom Dunn and Ivo Kokat, which are both of my promoters. Like I cannot really control it. Okay, yeah. So first we begin with a brief introduction about Bayesian and multi-objective Bayesian optimization. And then we started to having the main dishes, which is the PX2ES acquisition function. We discussed a sequential acquisition function setting, which is we try to do the optimization in a sequential fashion. And we also come up with a parallel acquisition function setting, which means that we want to try to sample multiple points in each iteration. And we come up with the empirical investigations on the multi-objective Bayesian optimization. And we end with the conclusions. And yeah, so if you have any questions during the talk, just post me and yeah, let me know. So what is Bayesian optimization? So Bayesian optimization is a kind of a efficient global optimization framework that tries to locate or identify the global optimum of a black box function under the low data region. So suppose like we really want to maximize a black box function f that we want to find the global maximum of it, and there are potentially can also having a number of constraints has been represented by this function g here. So under this problem, we are trying to find the maximum of this acquisition function, giving a really limited number of data budget, let's say. So this is actually in reality has a use case in reality is that, for instance, if you want to optimize a performance of a drug, for instance, the evaluation or the experiment you can do for different configurations of the drug, it has been limited because of the cost. So how can we really efficiently, hopefully finding the global maximum of the performance of the drug, only do a limited number of physical experiments. So basically, I think Bayesian fits into this kind of application scenario. And there are essentially two building blocks of Bayesian. So firstly, it's like, because we don't really have an analytical expression for the black box function that we want to maximize, based on the limited number of data we have, we build a statistical model there. So most commonly, we'll be using the golden standard, the Gaussian process, as a statistical model, which gives us a probabilistic distribution of f and g, or the objective and constraint at any unsigned input x. And how can we do optimize there? So the thing is we need an acquisition function that takes the input of this conditional distribution, as well as some sort of hyperparameters represented by this capital phi. And this acquisition function will capture or believe that where the global maximum of this black box function possibly be at. And of course, because there are uncertainties from this statistical model or the probabilistic surrogate model, or you can call it like the epistemic uncertainty from the model, we cannot really achieve the maximum by maximizing the acquisition function in one shot. So basically, we maximize this acquisition function, and then we sample making the query on the real black box function, and then we need to retune our model because there are errors on our model or the uncertainties. And this we do this iteratively, so we updated the model and making the new queries through maximizing the acquisition function, and do this iteratively once again until, let's say, we use up all our budgets. So on the right is an illustration of the base of how's it going on maximizing a one-dimensional function. And basically what we are saying, like through several iterations, we are actually able to reach the global maximum of it. And on the below is like illustration of different acquisition functions. So each of these acquisition function is specifically defined that you can use to plug in the base of routine. And the thing we want to highlight here is like different acquisition functions usually have different maximum location. So that means if you use different acquisition functions in your Bayesian optimization routine, it will have different performance. So the acquisition function development is actually a very active area in Bayesian, and is also what we want to come up with in this presentation. So in the multi-objective cases, instead of maximizing a single scalar value function, we are maximizing a vector value function. So come back into the drag cases. So if you want to maximize the performance of a drag, and at the same time, we want to minimize the cost of the drag, because otherwise nobody will pay for it. And these two performance measures are usually conflict with each other, so that we cannot really reach we cannot really have a X that reaches the maximum of the two performance metrics at the same time. So that means we need to sort of making a trade-off. And that is basically the idea of the difference of the multi-objective optimization. And how we can really compare the different candidates in the multi-objective cases. It has been defined by using some sort of dominance operator, which can be regarded as an extension concept of large, let's say. And so let's have a look at this right figure, which each of these dots stands for a performance measure of like a drag, for instance, in the objective space. And so how can we really measure one is better than the other? With the dominance really gives the hint there. It's like, so one candidate X is better than the other candidate X prime, in the sense that all of the objective function value of X is larger or equal than the second one. At the same time, at least there will be one objective that the objective function value is larger than the second one. So basically that is how we define the dominance. And with this definition, we can say that a feasible candidate include X. What we mean by feasible is that it satisfies all of these constraints. It's called the Pareto optimal candidate if there do not exist any other feasible candidates in the design space that are able to dominate it. So back to this right figure, what we are saying is like, for instance, take a look at this red scatter. All of these, or at least this part, the second objective function value is smaller than this one. So that, and also there is no actually one in this green scatter. That's objective one is larger than this one. So this is dominating this scatter dot. And all of these Pareto optimal candidates in the output space, in the input space, all of this Pareto optimal candidate will form a set, what we call the Pareto set, which is represented by the X of F. And its outcome is actually called the Pareto frontier, so which is what we show in this figure. So this red scatter dot is actually a Pareto frontier, or an approximation of the Pareto frontier, which has been constructed by the Pareto set. So in this, so eventually, if you do in a multi-objective optimization, what you get is like a Pareto frontier. That means there will be no other better solutions in this region. In this region, so you can actually choose one or two from the Pareto frontier with your preference. And this is like an illustration of the Pareto frontier in 3-dimension output space. And also in higher dimensions, you have different ways of illustrating the Pareto frontiers. So comes to our acquisition function to try to identify the Pareto frontier under the information-theoretic framework. So if we let the h of x, like a union of f and g, or the joint predictive distribution of the objective and the constraint, And if we're using a P of F representing the predicted distribution of the Pareto frontier, then we can actually come up with the mutual information between the Pareto frontier and the predicted distribution of the objective at the constraint. So basically, this is a standard formulation of the mutual information. And the thing is like if we plug in an approximation term, which is like a term Q here, and we split the logarithm, basically we have a second term that's representing the KL divergence between a P of H of X condition and we observe the Pareto frontier, as well as its approximation Q. And if we have the reasonableness to say like we have a Q as an approximation of that conditional distribution, we can actually throw out the KL divergence term. So eventually we'll obtain this last line of equation, which what we call the information lower bound formulation. And the thing now is becomes like we only need to handle the approximation of the conditional distribution by observing the Pareto frontier or the F. So now the goal becomes like how to have a reasonable approximation of the conditional distribution, given that we realize the Pareto frontier. And how do we really having a reasonable approximation here? So here we really do a approximation in a truncated fashion way. So what we say is like, okay, let's remember that we earlier showed this red scatter dot as representation of the Pareto frontier. So if the Pareto frontier is really looking at something like this for this problem, it means actually we shouldn't have any probability, or we shouldn't really have a scatter dot in this region, because otherwise the Pareto frontier is not well defined. And the same, this is actually the same thing. What we can make use of for this approximation is that basically we can, given that if we have a realization Pareto frontier, which has been represented by this red curve, the objective space can be partitioned into two parts. So one part is that this region that we're actually representing that where this grid scatter is located in, and its complement, which is what we call this, the yellow shaded region, or the region of A. And this region of A is just a region what we call the non-dominating region, because if you have any point in this region, it actually will dominate part of the Pareto frontier, or it will become a new Pareto optimal point that has been located on the Pareto frontier. So with this thing, keep all of the thing in mind, the approximation we came up is like has been shown there in this kind of segment function, that basically we shouldn't have any probability in the yellow shaded area, otherwise the Pareto frontier is not well defined. Of course, this actually having an implicit assumption that we do this approximation by only considering where we are located at. So basically, we are considering at the X. We come up with this later in the end of this presentation. That's it. So basically, this is like a truncated distribution that has been truncated by realization with Pareto frontier. And the normalization constant is just stands for the probability of being in the non-dominated region, or the probability of being in the yellow shaded area. Ideally, this yellow shaded area doesn't really have an upper bound. So basically, this triangle should be infinity. So and as well as this scatter dot also should be minus infinity. So that will be the partition of the objective space. And if we plug this approximation in the information lower bound, eventually we will having a reach the acquisition function, which has been written as the expectation of the Pareto frontier distribution, while inside is just a logarithm of 1 minus the probability that of being in the non-dominated region. And this actually gives a very nice explanation of this acquisition function, is that if we focus on the inner part of expectation for a moment, basically we are only dealing with is just this normalization constant, or the probability of B is a non-dominated region. So this BA, this normalization constant actually stands for a well-known acquisition function in multi-objective optimization, what we call the probability of multi-objective version of probability of improvement. So basically, what it means, like if we have a direct delta distribution in our realization of the Pareto frontier F, that means we ignore the outer expectation, then this will be exactly the same as the multi-objective probability of improvement. That means the acquisition function will reach the same maximum at the same. So basically, it will stand the same in the input space. And actually, this is a very nice thing because just want to remark is that a lot of information-theoretic acquisition function relies on exhaustive approximations. And eventually, if you do too much approximations, like a factorization-based approximations, then eventually it's a bit difficult to explain the acquisition functions. But here it's really have a nice link with the existing acquisition function that does not really rely on the information-theoretic framework. So how do we really calculate the normalization constant or the probability of being in that non-dominated region, the yellow shaded area? The main difficulty is the realization of the F actually does not really having an analytical expression. So basically calculating the probability of being in this area is really a bit painful. And what people mostly come with is actually a discrete approximation of the Pareto frontier. For instance, if this red curve has been approximated by the 5 stars, the red 5 stars, as a discrete approximation of the Pareto frontier, then with a very common technique, which is called the hypervolume-based decomposition in the objective space, we can actually approximate the yellow shading area by decomposing this decomposing the non-dominated region into this the union of these 4 disjoint rectangles.
Sorry,
yeah,
this is maybe a silly question, but given that those rectangles go out to infinity, surely the area is just infinite.
So yeah, the thing is like the answer is yes. And the second thing is basically eventually we will only need to calculate the probability of being in this region. So it's like CDF of infinity, and that's still something we can handle. And the second thing is for other acquisition function in multi-objectives, they also do this. But in practically, they will have a ideal point, which is not located in infinity, but somewhere that is a little bit shift from the Pareto frontier. So it's finite. And this is like you can consider it as like a hyperparameter of the acquisition function, which is capital phi that we have shown before.
Okay.
Yeah. So this partition in its 3-dimensional output space is also illustrated in this figure. And you can also do it for higher output dimensionalities. So basically, we make use of a hypervolume-based output space partition strategy to partition the output space into NP disjoint hypercubes as the approximations of the original not tractable non-dominated regions. And this also holds for if we have a constraint. So if we have the constraint, let's say, and we follow the formulation we did before, that constraint is larger than 0, we can partition these observations by first doing it we ignore the constraint, that we will have these partitions, and then we sort of come back with the constraints. So because the constraint is larger than 0, representing that is favorable, so that we're really having these regions. But this basically is doing the same thing as without the constraints. We just only need to concatenate the constraint at the end of these partitions. And then if in the constraint cases, basically the non-dominated feasible region, which stands for that you are both non-dominated and at the same time you need to be feasible, that means we satisfy the constraint, will be the region that has been represented by this the join of these cubes. So given these approximations, we are really actually things will be much more easier, because then the probability of being in the non-dominated region can be written down as an approximation, as a summation of the probability of in each of these rectangles or hypercubes in higher than output dimensionalities. and the I tilde is just a probability of that each of these rectangles. And if we assume that each of the output, each of the objective function and the constraint is statistically independent, which means it doesn't really have correlation between them, basically the probability of being each of these rectangles can be calculated in a very simple form. And the things like, one thing to remark here is like this AIU K of a complex, but it's just the value of the upper bound at like, so if this goes to infinity, this will be still calculatable. So that comes back to the question that whether the infinity will be something not very handleable. So eventually, actually, the acquisition function will be written down as this form, where basically the normalization constant has been approximated by the summations. And for the outer expectation that we do the expectation through the Pareto frontiers, basically we can also do a Monte Carlo here by making use of, so say we are doing all of the optimization in the GP, then we can approximate the GP by using the Bayesian linear model and do using a standard multi-objective Bayesian multi-objective optimization algorithm, like meta-heuristic algorithm here to optimize the continuous trajectory to get the approximations. So basically, this is how we do the outer approximations.
Like the stars that you have, are these points you've already acquired and you know from your data set that are currently the Pareto optimal points from what you currently have, or you determine this location of stars?
We define it based on, so let's say, because this F is actually relating to the outer expectation. So we basically, practically speaking, we sample the Pareto frontier from the GP, and then we calculate the Cartesian or what we use right here to calculate this star. So it's based on the sample of the GP, not exactly from the data we already sampled. Yeah.
So does it also plug with the Qing sample dimension? It's like the observation values are on themselves with.
Yeah, it's a good question. Well, unfortunately, I have to admit, actually, we haven't really considered the output noise. But the things like, for here, let's say, because, let's say, if we use a GP, which we have the predictor of F, which is the latent function, which assume that noise free, we can still do the sample on the F, which, based on the F, the latent function, which will give a noise-free Pareto frontier, right? Does that somehow answer the question?
Yeah.
So yeah, the outer expectation basically has been approximated by running the multi-objective optimization algorithm on the GP parametric approximations. So yeah, this technique has been basically proposed by the predictive entropy research. So this comes to the end of the sequential acquisition function. In the parallel setting, since actually will be the same, we still need to approximate the Q, which is like the predictive distribution based on joint. So the parallel setting, what we mean is like, if you want to do Bayes-off in the sense that we want to sample multiple points at the same time. So come back to the drag cases. If let's say people have the parallel resources, you can really test the drag performance. You can really test several drags performance at the same time. You'll probably not want to really do this acquisition function maximizing in a sequential manner, because if you can really give me several drags for me to test, then they will be perfect. So the parallel scenario is basically proposed for that kind of application cases. Now here we need to consider is like how do we really have a reasonable approximation Q that we have in the Pareto frontier. That actually will be difficult to visualize even for the batch size equals 2, because then we have a 4-dimension output to visualize. So here we actually visualize giving a visualization, which is a single objective based. So basically the first axis is the batch element 1, the predicted distribution, and the second axis is the predicted distribution of batch element 2. And if we know that, for instance, the optimal point is located at here, then the truncated distribution will be something looking at this one, because we don't really we shouldn't have any probability density in this region. This region stands for any of this static element is larger than the optimum that we have had at hand. So basically come back, so QTF squared yes will also be something written as this. So only difference is like the VA tilde Q is actually an extended concept, and it actually stands for the probability that exists at least one batch element that is in the non-dominating region, or in this A tilde 1 to A tilde 4, let's say. And this is actually a probability distribution that is a bit difficult to handle, because we have this at least, and we also have the union of the joint of these rectangles. So eventually, actually, has also been replaced by this max, and the indicator that the event that stands for is located. If it is located in this region, it's like this event has been replaced by the indicator function, which has been approximated by the product of this signal, which stands for like is smaller than the upper bound of the rectangle. And so yeah, it's smaller than the upper bound of the rectangle and larger than the lower bound of the rectangle. So that stands for the it's inside this kind of rectangles. And this is how we came up with this approximation. And you know, if you do the multi-color approximation for every input candidate X, the acquisition function will become difficult to optimize, because for each this optimization usually has been driven by a first order optimization technique like LBFGS, and then if we really redraw this multi-color samples for each input X, then the gradient of this the acquisition function will be quite noisy, and basically we cannot really perform optimization here unless, let's say, use some add-on, for instance. So what people usually do here, and we also do it, is like using a reparameterization trick to kind of reparameterize this approximation, and eventually we have an acquisition function that's a bit easier to optimize. So as a proof of concept, this is like a illustration of how the batch acquisition function performs. So the first row stands for so these are the input, and the horizontal axis is just the X, and vertical axis is X as well, because we have a batch size of 2. And this probably doesn't really have too high resolution, but I hope that is sort of available. So the second row is like stands for where we sampled is objective space. And these different scatters are the GP sampled Pareto frontiers. And this black where the batch samples are located. To getting close to each other means actually the uncertainty of the Pareto frontier has been reduced. And what we can also show from the last figure as an application, as let's say, if you want to really make use in applications, that we propose a recommendation of the Pareto frontier based on the GP. And here is like at the beginning, the recommendation is quite bad because there are some false positive Pareto frontier. So basically, some point has been recommended by GP. Actually shouldn't be the real Pareto frontier, but has been really recommended. But in the end, actually, what we show is that this GP recommended Pareto frontier is really accurate, as there is no false positives. So we came up with the empirical validation of the PF squared yes. So first we conducted numerical experiments on the unconstrained multi-objective Bayesian optimization. So we don't really consider there are constraints. The first row stands for the sequential acquisition function scenario. And the second rule stands for the batch scenario that we can sample 2 points per each iteration. And we compare a lot of different acquisition function that has been proposed for multi-objective Bayesian optimization. Most of them are actually also information-theoretic based. And this is what we have seen. Basically, our acquisition function performance is represented by this orange. Yeah, so you can see this here and here and here and here. So in the batch cases, it will be also shown in the figure. And there's also only one thing we want to remark here is like for the last 2 benchmarking questions, validity 1, validity 2, actually objective scale is highly different. So what we mean by this is like, okay, for instance, the cost of the drag is actually something millions, and the performance of the track is something probably scaling from like 1 to 10. Then you will have a different scale of the objective. And in these cases, this will actually affect the hyperparameter of the fee that the acquisition function will take. And this, well, while this is not for our cases, for our acquisition function, but for other acquisition functions like the EHVI and the QEHVI, which is considered as a golden standard acquisition function for multi-objective Bayesian optimization, which needs this kind of hyperparameter, and this hyperparameter is really sensitive to the scale of the objective. So what we say here is basically you see actually surprisingly this acquisition function performed quite bad. This is because the hyperparameter that's corresponding to the scaling of the objective has been misguided, let's say, because of the different scales. And yeah.
The question: do any of these multi-objective acquisition functions take into account the covariance or the correlation between outputs? Or do all of
yes, they do. So there are papers like I think, there are papers really consider this.
Do any of these problems benefits from having this?
We haven't really tested on this scenario, but I think people usually do is also try to having a, let's say, a multi-output GPs that basically capturing the correlation between different output, and then you can also basically optimize the acquisition function there. And most of the cases in that scenario, people do is basically build the acquisition function based on the Monte Carlo samples. So the predictive distribution is sampled by Monte Carlo, and then we calculate the acquisition function based on that.
Would your approach also allow for this? I guess it is, right? Because the expectation of the Pareto one could capture this.
Yes, then that will be like we need to do something on the parametric sample of the GPU. To, let's say, the sample need to capture the correlations. And as well, before we actually show a product of CDF, product of subtraction of CDF, and that will also be affected by the correlation, I guess. But yeah, that's actually a good spot. So for the constraint multi-objective Bayesian optimization, we also compared different acquisition functions. Again, the first rule would stand for the performance on the sequential cases that basically we compare these different acquisition functions. And the second row is like the batch cases where we have a Q equals 2. That means we want to sample 2 times in the same iteration. And there's also one thing to remark is that especially for the C2 DTLA2 problem, that the Pareto frontier is disjoint. What we mean by this is actually has been represented by this figure. That you can see that it actually ignore this scatter plot of the Pareto frontier of C2 DTLA2 will be this one and this one and this one. So it means actually there's like a spacing between the sub-Pareto frontiers. And this will also actually cause a large issue to the hyperparameter of acquisition functions like the EHVI series. This is because it's really sensitive to that kind of the shape of the Pareto frontier. Well, again, the EHVI and QEHVI are somewhat also considered as a golden standard. So that's a great reason we want to mention more about it here. So again, for that acquisition function, we need the triangle that we showed before to be somewhat close to this Pareto frontiers. And then this triangle cannot really know like how the Pareto frontier looks like. So it can actually locate it here or here or here. And this will cause the acquisition function behaves quite bad. So that is the reason, again, we should add the EHVI off and the EHVI looks quite weird, which is the blue curve. That's what we're talking about. So yeah, basically that's given by this remark. Information-theoretic acquisition function based on the lower bound of the mutual information, and also supporting sequential query, and also the parallel cases. And parallel has been powered by Monte Carlo approximations, as we mentioned before. And you can use it for based on with or without the constraints. And the acquisition function also has a very close link with the multi-objective probability of improvement. Hence, actually endowed a very nice explainability. For other output-based multi-objective information-theoretic based acquisition function, unfortunately, I think there's no such a nice explainability yet. So the main empirical advantage of PF squared is compared to other greedy acquisition function or the golden standard EHVI or this kind of yellow shaded curve, shaded performance curves we have seen in the previous slides, is that it's actually free of specifying a reference point or the hyperparameter of the acquisition function. So this is important in the sense that you really have a problem that your different objective scalings are quite different because this actually happens. And or the second is like your Pareto frontier is disjoints, as we're saying from the constraint cases. So the main limitation, I would say, is like the first is that we having the approximation of the predictive distribution of H of X conditioned by the Pareto frontier is like we are still doing it in a way that we only impose a condition on a given X. So in reality, or in the GP cases, actually we need to really consider this constraint for all of the design space. But unfortunately, due for computation convenience, what we are doing is like only condition on a single point. And probably there are some constraint GPs can be making use of this topic, but we haven't really got that deep. And the second thing is the definition of the distribution of the Pareto frontier. So Pareto frontier is ideally is actually infinite dimensional stuff. So the red curve that we have seen before is actually infinite dimensional because, but in practice, we usually do it is like a dual approximation because it's also needed to make the mutual information somehow well defined, I guess. But there probably are some debates on whether this P of F is somehow reasonable or not. And regarding the empirical and application wise, I would say, yeah, as mentioned, it's like the current approach we came up with hasn't really been able to handle the noise. And also the itself with the number of output dimensionality. So normally you can do it for 3 and up to 3 and 4. But I guess if you really have a high dimension output objective problem, like if you want to consider the performance of the drug, if you like have 10 different performance of the drugs, then basically this will be something not handleable by making use of this acquisition function, I would say. But yeah, but again, this is not a unique issue of this acquisition function because a lot of other acquisition functions like the EHVI we have mentioned will also have this limitation because all of them are building on the same hypervolume based partition strategy. And another thing is like the scalability of input dimensionality is also somewhat limited. This is mainly because so information theoretic acquisition functions that we really want to reduce the uncertainty of the quantity of interest, let's say the Pareto frontier, we are defined here. So the sort of ideal way to use the recommendation is not based on where we have sampled, but we really want to build up our belief about where the Pareto frontier is by optimizing the GP posterior mean, let's say. And this is what they call the out-of-sample recommendation. And the issue with out-of-sample recommendation is that they need to really rely on a very sort of accurate GP model. So in high dimension cases like 8 and 10, basically there are some sort of issues with the GP accuracy, and then the recommendation probably cannot really having a very accurate recommendations. So that means you're probably having some false positive Pareto frontiers or false negative that you ignore some of the Pareto frontier. And of course, there are some upcoming researchers tackling this by formulating the entropy in a different way, as given by the reference to, I think it's last year's NeurIPS, which built a sort of new entropy on the doing in a more end-to-end way. Yeah, so I guess that's all the stuff. Thank you for concentration. Yeah.
Maybe I can ask something. I find this quite interesting that you use this probability of improvement.
Yeah.
And I was thinking how this method would generalize to the one which I guess I mean it's just to think about analogous things. And I was thinking that usually people don't use probability of improvement that much in the 1D case because it really just use the
of the Pareto frontier.
Yeah, I mean, in one dimension, the sample from the Pareto frontier will be just the one maximizer.
Yeah.
And then if you sample your one data point that is the maximizer, and then you do, okay, now I was thinking, and then you do probability of improvement, you will be always placing the highest value at the maximum.
Well, the thing that you mentioned about the greedy stuff, greedy property of the probability of improvement is indeed actually what we also observe here. So yeah, we haven't really having the content at least in this presentation, but in the paper, it's like there are issues because exactly for the greedy stuff that you mentioned. So let's back to this slide, back to this slide. So if let's say the Pareto frontier has been represented by these 3 red 5 stars, if we calculate the probability of being in a non-dominated region, there is actually one issue is like it can locate it, for instance, here, and it will really having a high confidence that can make the improvements. So yeah, this is basically an issue that we really observed and at the beginning and really actually hinders the performance of the acquisition function. So what we actually try to mitigate is like to use as a very simple technology in the sense that people use to handle the probability improvement by shifting this Pareto frontier a little bit to that. We came up with 2 approaches, but the one we're making use of is like we shift it with the shifting vector defined by the percentage of the variance of the Pareto. So let's say the maximum subtract by the median. So that's a range of the Pareto frontier, and we use a percentage of that as a heuristic way to shift and use the probability of improvement deal. And this somehow mitigate the greedy issue. Yeah, with the greedy issue, actually, this is really it really actually the acquisition function with the greedy issue is not performing well. So that is the reason we use this. But yeah, indeed. This is something we also observed in the empirical experiments.
Cool. If there's no other questions, let's thank Jixiang again.